We are now recording. Let me get the setup from the current slide. And let me go over a couple of other sort of last minute announcements. Number one, they have opened student course evaluations. So please do those as soon as you can. If you want to wait till the end of the term, you can, but just don't put it off too long and forget about it at the end. Please do the student course evaluations. And the other thing that I can think of now is my office hours a day should be normal, 3:15 to 5:15. However, on tomorrow, normally my office hours are 10:45 to 1:15, but I have a luncheon meeting that's going to be going from something about 11:15 to 1. So that basically wipes out almost all my office hours. So if you do need to see me, try to catch me right after 10:45, because I'm probably going to have to leave by 11 to get to the meeting by 11:15, or catch me right before 1:15, because I'll be rushing back from the meeting, or it could be conceivably in trying to get to my 1:15 class. So try either time there. Now, the other possibility here is that my class tomorrow afternoon will have a lab, and it goes supposed to run 3:45 to 5:45. I'm guessing they're not going to take a full 2 hours. So if you do need to see me and can't catch me either side of that lunch meeting, probably from 5 o'clock and maybe even before 5 o'clock on, I'll be pretty free, because I think they'll be through with the lab before 5:45. So around 5-ish or so, I might be able to be available. All right. Any questions on anything we've done up till now? All right. We're on in Chapter 14, Differentiation in Several Variables, 14.2, Limits and Continuity in Several Variables, and Example 5 on page 753. So let me just blow this up. Not going to try not to spend a lot of time on this one. It's one of those sort of strange ones. This is the function f of xy is equal to x squared over x squared plus y squared. Obviously, a function with two independent variables, one output or a dependent variable, z or whatever you want to call it, but it's the function value. And here's the issue. If you look at the values here, you can see that the limit doesn't exist. Now, what they did, they plotted a few, and certainly when x is equal to any value in the world and y is equal to 0, then this gives you x squared over x squared. So for all y is equal to 0, this is y is equal to 0. That's what this column is. And x equals 0 is this column. So here are your answers. 1, 1, 1, 1, 1, 1, 1, 1. Now notice they left this out because x equals 0 isn't defined. All right. Now, if you let x equal 0, but y be any other value except 0, then this obviously is going to be 0 over y squared, which is going to be 0 for all x equals 0s, except, of course, where y is equal to 0 as well. Not defined there. Now, you try other things like x equals y. That would be the diagonal values here. So when x is equal to y, this would be 2y squared down here and a y squared up here. 2x squared down here and an x squared up here. That's 1 over 2. So 0.5 are your values on the diagonal, okay? And on the anti-diagonal, same thing, because if it's minus x is equal to minus y, doesn't matter. This is still x squared over 2x squared. So 0.5 down here. Notice the values are always positive because everything's squared, so they're always positive. So basically what you've got is a situation, as you're coming in this path, your values, the limit looks to be 1. Coming in this way, it looks to be 0, 1, 0, 0.5, 0.5, 0.5, 0.5. Obviously, there is no limit at the center. Okay? So this is a function that doesn't have continuity at the center at all. Okay? There is no limiting value there. Now, that's one way you can approach it, and that's basically what this describes for you. I don't want to spend super amount of time on it, but that's just one where the limit doesn't exist at 0, 0. Nowhere close. Here's example 6, I believe. And oh, no, I'm sorry. This is also the same as the one we just had. It's just the figures and such as... No, I'm sorry. Yeah, this is... Yeah, the top graph... Well, no, this is the figure we just were looking at. And it just shows it in a different perspective. Obviously, z is equal to 0. You have a variety of values. I mean, not x and y equals 0. You have a variety of z's. It's just not at all possible. And these show the same thing we did before. C is equal to 1 if you go in the x-axis from either direction. 0 if you go in the y-axis from either direction. And everything between 0 and 1 as you go this way or that way or that way. I mean, everything you got a variety of values there. So yeah, it doesn't exist. The values for z will be between 0 and 1 everywhere. But no fixed value at z. Okay. So that was the end of example 5. Here is the one for example 6. Okay. Now, here's your function. Thank goodness I didn't have to graph this, they did. The graph of f of xy is equal to xy squared over x squared plus y squared. Okay? Now certainly there's a hole in the center. X can't be 0, y can't be 0. Okay? But can you, is that a, what do they call it? I want to say replaceable. That's not quite the word they use. That you could plug in a value there and make it continuous everywhere. Because x0, y0, you're still dividing by 0. But if both x and y isn't 0 at the same time, let's take x equals 0, y not 0, then that would be the y-axis, and where x equals 0, y not 0, you're 0 everywhere on the y-axis, positive and negative. When y is equal to 0, x not 0, again it's 0 everywhere on the x-axis, except at the origin. Okay, not defined there. Now, how about those other points coming in from the other angles, like x equal y? Well, let's make this y cubed over y fourth, right? X is equal to y. This would be y cubed. I'm sorry, this would be 2y squared. Okay, y cubed over 2y squared. Well, as x approaches that would be, as long as x wasn't equal, y, I was saying y. As long as y isn't equal to 0, that would be approaching y over 2, okay? And y over 2 as y is getting smaller and smaller and smaller, that would be going to 0 as well. So it does look like that would be a differential except at the origin, not defined there, but you could substitute in there 0, z is equal to 0 there, and that would be. So it would have a limit there as you went. Now, that's the end of the slideshow for 14.2. Do you want to do preliminary questions? Are those helpful to you? Would you like to do those? Yay or nay? Yes? Okay, let's look at those quickly. In case I do have to write some down. What is the difference between D? Okay, let me get my pen activated. There we go. D of PR and D star of PR. What's the difference between those two? Okay, yeah. The D star does not include the point P. D does include the point P. Okay? That's basically it in a nutshell. Okay? Let's see how they phrase it to see if there's any other. This is what, 14.2? 14.2. D star consists of all the points in D without the star other than the point P itself. Okay? And in the back of the book they have lowercase p, and this they have uppercase p, whatever. P is a point. All right? Now, number 2. Suppose that f of xy is continuous at 2, 3. Okay? And that f of 2y is equal to y cubed. Okay? For y not equal 3. Okay? What is the value of f of 2, 3? What is the value of f at the point 2, 3? Any guesses? Okay. And what would that be? Hazard a guess? Yes? Okay. Now, they said f is continuous at 2, 3. So that means you can't have any major breaks or holes or anything else there. Is this one of us or not? Who was it? somebody took it on themselves. Yeah, the numbering of this building, if you haven't noticed, is a little strange. Okay, right? And classrooms down the hall here, you know, on the outside, there's more rooms than on the inside the curve, right? So there's a 254, it's the first classroom on the right as you go down, you know, once you pass the passageway to go to the natural services and that part. And then you got 256, and that's all. Well, there's two offices between. They don't number the offices. I don't know why. So someone at some time in the past put the first office is 255A and the second one is 255B. Of course, there aren't any odd numbers on that side of the hall. Someone just did that. And Dr. Thomas' office is the second one of those. So that student was looking for Dr. Thomas, and this is room 255. Those are not 255, someone just put that down somewhere. So that's probably why that came from. It's bizarre. Okay, what we have is f of xy is continuous at 2, 3. And we know that f at 2, any value y, is going to be y cubed, except possibly at y is equal to 3, or when y is not equal to 3. So therefore, as y gets closer and closer to 3, this is getting closer and closer to, oops, I can't mark you with this. Marcus is here. Yes. Okay, well, I'm in class. Oh, okay. All right. Why doesn't he come talk to me? Why does he send messages? I don't know. Okay. So as y is getting closer and closer to 3, what is this getting closer and closer to? Not 9. 27. And because it's continuous, as it's getting closer and closer to that, that must be, for it to be continuous, it must be 27 at that. Okay? If it wasn't continuous at 2, 3, it could be anything. But this says it is continuous there, so therefore the limit as y approaches 3 must be the value of that. And the limit as y approaches 3 would be, it doesn't matter what x is, y would be 27. Okay? That was 2. Does that make sense, sort of? Okay. Number 3. Suppose that q of xy is a function such that 1 over q of x, okay, let me write this down. I think I'll erase this. We're doing the preliminary questions for 14.2 on page 755. Okay. Suppose that q of xy is a function, obviously, such that 1 over q of xy is continuous for all xy. Okay? Ordered pairs xy. Which of the following statements are true? A. Q of xy is continuous for all xy. B. Qxy continuous for xy not equal to 0, 0, the all others. Or C. Q of xy, well, Q of xy is not equal to 0 for all xy. Which of those do you think are true? Now, by their subject verb, it almost suggests that more than one could be true. I do know at least one is true. Let's see if more than one is true. Yeah. Okay. C definitely is true, okay? Because this can't be 0 for that to be continuous to all x, y. Okay? Now, does that mean the other two aren't true? Well, we don't know that for a fact. Let's see. If q of xy was not continuous somewhere, then 1 over q of xy I don't think could be continuous either, right? It just doesn't seem like it could be. So A kind of has to be true too, and certainly if A is true, if that's true for all xy, it certainly would be true for xy not equal 0, 0. So I think, yeah, and in the back they say all three are true, which it's a little, it's hard to, if you can come up with one example of why it's not true, you can say it's not true. But if it's always true, it's hard to come up with every example that says it is true. Yeah, so that one, that's a little on the hard side to prove, okay? Let's look at number 4. Again, I think I'll start with scratch on this one. Okay, so we have plenty of room. Suppose that f of x0 is equal to 3 for all x not equal to 0. F of x0 is 3 for all x is not equal to 0. And f of 0y is equal to 5 for all y not 0. Okay? What can you conclude about the limit as xy approaches 0, 0 of f of xy? What can you conclude about that? Anything? Say this again. It does not exist. I believe you're correct. D-N-E does not exist. And why is that? Well, if you think about this, here's your xy. That's not that graph. But f of x0, that means when y is equal to 0, y is equal to 0 everywhere on the x-axis, right? So f of x0 is equal to 3. When no matter what value x is, so you're up here at 3 here and 3 there. Except at x equals 0, we don't know that. Anything there. But from every other, from both sides of both ends of the x-axis, the function is equal to 3. But when x is equal to 0, for all values y, except y is equal to 0, then this is 5. So it's 3 coming this way, 5 coming this way. What's the limit as you're approaching? No way it can have a limit, because it's 2 apart from this direction and that direction. No way it can exist. So does not exist, I think, is a very, has to be the answer. And it says, yes, it does not exist. All right, homework exercises here. Do any of the odds 1 through 7.
do either 9 or 11 or both. Any of the i's 13 to 17. Either 19 or 21 or both. Do 23. Do 25. And any of the odds 27 to 39. And either 41 or 43 or both. 43 looks like it's just sort of a think-through problem. There may not be any actual calculation. All right. Enough of that, okay? That's just the background stuff that is good to have in hand before we hit 14.3. This is where the real meat of the chapter and what you need to know is. Partial derivatives, if I can ever get it to come up. Well, it doesn't. Oh, there it comes, maybe. Yeah. All right, slideshow from current slide. And get my pen color back. And before we hit this, let's do here. We have stressed that a function f of two or more independent variables does not have a unique rate of change because each variable may affect x in different ways. For example, the current I in a circuit is a function of both the voltage and the resistance. So you could say I is as a function. Okay, let me bring that up just a little bit. That the current is a function of both voltage and resistance. Okay, and we know what that function is, V over R. If you've had physics, if you haven't, still true. Ohm's law says that. Current is a function of voltage and resistance as V over R. Now, as you increase the voltage, your current's going to go up when the resistance is constant. If you increase the resistance, the current's going to go down if the voltage is constant. So you see current is increasing with an increase of V, but decreasing with an increase of R. So it's going different directions depending on what variable is doing what. Okay? What we're dealing with now are partial derivatives, and here basically is your format for them. Hopefully you'll notice the similarities between them and derivatives. At first glance, the only difference, well, maybe not the only, the main difference is a subscript. Okay? Now, here we have a function sub x. And I haven't told you what that is, but I'll tell you. It's the partial of this function, the derivative of this function, with respect to the first variable, the x, when x is equal to a and y is equal to b. So it's how that function is changing with respect to x. Doesn't matter what's happening to y with respect to x, as x is at x equal a and y is equal to b. And the definition for that, just like I hope you would expect, is the limit as h approaches 0 of f of a plus h comma b minus f of a comma b. Because we're not changing b, we're only changing the x, and we're not changing y, we're changing the x, and we're changing that by the amount h. So this would be that limit, partial of that, as h is approaching 0, a little bit beyond a coming closer and closer, whichever direction it is. F sub y, that's the partial derivative of the derivative of y of f with respect to y at the point AB, when your a is not changing, but b is allowed to change from b plus k to b, and that would be that partial. Okay, that's the definition of that partial derivative. Okay. Now, here's a little bit of a problem. Not a major thing. You should be used to it by now. Okay? But here's what it is. These partials can be written so many different ways. One way, as you just saw there, is f sub x, partial of f with respect to x. So this could also be written as the partial of f with respect to x. Now, notice we're no longer writing our d for derivatives. Because this is a partial derivative, we put this curly q d, and that's called the partial. Not the derivative, but the partial derivative of f with respect to x. That's the same as f sub x, okay? And the partial of f with respect to y would be the partial of f with respect to y, okay? Now, if you're evaluating it at a place, then you could put the point here, AB, and then this could, bless you, could be written as f sub x evaluated at AB. Okay? And same thing here. If this is at the point AB, this would be the partial, f sub y evaluated at AB. Okay. So just different ways to express that. Now, if we had said this f function here would also be your z variable, then you could solve this as partial of z with respect to x, or partial of z with respect to y. And what it means there, how is z changing, or the function changing, when only the x is changing, and how is it changing when only the y is changing? And that will give you that. Now, here is the secret. And if you remember this, you almost have it knocked. And it's not really that big of a secret either. Notice when I was saying that, how is function f changing when x is changing? What is understood there? You're not changing y. Y is treated as if it's a constant, not varying. And here, how is f changing, or z changing, and the y is changing, given the x is not. And that's the key. When you're taking the partial with respect to one of multiple independent variables, you treat all the other independent variables as if they're constants. You're not messing with them at all. And that's the key. So, let's do example 1. I think I will clear this out. And here's your function. F now is a function not just of x or just of y, but of both independent variables x and y. And this function is x squared y to the 5th. Okay? So, what's the partial of this function f with respect to x? Listening carefully to what I just said, when you're taking the partial of a function with respect to one variable, you treat any other variables as if they're constants. They're not variables, they're just a constant. So guess what that would be then? Two x y to the 5th. You take the derivative of the x just like you normally did, but think of that y to the 5th as just a coefficient. It doesn't vary, it doesn't change, it's just there. So if you really thought of it as a coefficient, you might say 2y to the 5th times x, okay? If this is your exponent and that's your coefficient, 2y 5th times x. But most of the time we leave it in order. All right, very good. Same function f, what is the partial of f with respect to y? Five x squared y to the 4th. Perfect. Perfect. Okay? Now, in your book, or at least in my book, when they write it out several different ways, after the second equal sign of that last one that we just did here, they have partial with respect to x, which is totally wrong. It's partial with respect to y. I don't know if your books have that or not. Does yours? I know you have the loose leaf. Yours is the later printing. That last line on page 757, bottom of the page. Partial of alpha with respect to y is equal to blah blah is equal to x squared partial of y fifth with respect to, what does 0 say? Yeah, that says x. I assume all of you have it wrong, because that yours is the most current printing I know of. Okay. Any questions on that? Now, they do a little bit of a graphical insight here, and let's just imagine I can't get this to move well. Okay. Here is your function. We don't give a name for it. Let's just say that's your alpha of x, y. Yeah, alpha of x, y. Okay. That shape, that parachute, whatever it looks like. Okay? Now here's a point, x equal a, y is equal to b. There's a point a, b right there. The function at that value a, b, these are independent variables here. The function there is this value up here, alpha of a, b. So the point up here is a on x, b on y, and alpha of a, b on z. Okay. Now, what are the partial derivatives of that? And this is why we were messing around for the first part of this chapter with trace curves again. Because if you're taking the partial of this with respect to x, with y being constant, you treat the y equal b if it's a constant here, and then you're doing the derivative of that curve right there, okay? And that would be its derivative. Some positive number there, that would be its derivative. That trace curve for y is equal to b of that surface, that one trace curve, that would be for y is equal to b, take the partial of that with respect to x, and evaluate that at a. That would be the slope of that line. Okay? So there's the partial derivative of your function with respect to x when b is held constant. I mean, y is held constant at value b. Oh, yuck, I did that again. Keep hitting the wrong. Okay. Now, if you take the partial with respect to y of that function, with x being a constant, and at this point x is equal to a, it's not changing any, then here's the plane where x equals a, okay? And then the partial of this function with respect to y would be that curve. Now, it would be y would be anywhere, the curve anywhere here, but at the point AB, you already got your A, then you come out here on B, and that gives you this, so there's your slope. The partial of y with alpha with respect to y at AB would be that slope. That happens to be a negative slope there. Positive slope with partial, no, I'm sorry, that's partial there. No, it isn't. That's a negative slope there too. You have to look at it from this perspective. Going down in z as x is increasing, and this is going down in z as y is increasing. So both of these have negative slopes at that point P. At some other point P, they may not have negative slopes. Okay? But you do the trace curve, in this case for y is equal to b, in this case for x is equal to a. Okay? Does that kind of make sense? That's why we did all that on trace curves again, to refresh that in your mind, because that's what you're counting on. Okay. I think this is example 2. Here's your g of x, y. Y squared over 1 plus x squared cubed. Okay? It says calculate g sub x of 1, 3, and later we'll calculate g sub y of, I'm sure it's 1, 3, 2. Yeah, there it is, 1, 3. Okay? Guess what you got to do first? Help me. What will you do first? Okay, let's take the partial with respect to first x and then with respect to y. So let's do partial of g with respect to x. And we'll just do it of xy to begin with. What would that be? Partial of g with respect to x. Before I did that, I would do this. Write this as 1 plus x squared to the minus 3 times y squared. Okay? Because I don't like to take derivatives in period in general using quotient rule if I can avoid it. If I can write it as a product rule with exponents, I'm going to do it that way. Okay? Now, with it written that way, can you give me an idea of what partial of g with respect to x is? Negative 3. 1 plus x squared to the negative 4 times what? I can't hear. 2? Where'd you get that? Second? Okay, that would be a 2x, wouldn't it? Okay. Because there were 2 2's there, I wondered where you got them from. You through? Times y squared. Got it. So if we pause and sort of clean that up a little bit, in your numerators, you got a minus 3, a 2x, and a y squared. So let's make that, let's put the minus out front, and that would be 6xy squared over 1 plus x squared to the 4th power. Okay, I think that will be the simplest way to write that. But now let's do it. They didn't ask for it in general, they've asked for it at 1, 3. So what would that be? Minus a little louder.
6 times 1 times 3 squared.
Okay. Yeah, let's see. Okay, written that way. Yeah, that would be minus 6 times 1 times 3 squared, which would be a little louder. $54. Is that right? Over No, I'm sorry. I was taking a radical. There's no radical there. It would be, I can't hear you, 16. Which would then be, I think we can reduce that a little bit. All I can see is 2, so that would be 27 over 8, I think. Let's see. Yeah, negative 27 over 8. Good for them. Okay? How about g sub y? I thought I had, oh, there it is. I see it now. Okay. What would that be? 2y. Yeah, but you don't even need to do that. Just write it that way. Okay. Because nothing, taking the partial with respect to y, you're not using the x's at all. Leave them down there. They're just numbers, you know. Okay, constants. Okay, now let's do that. G sub y at the point 1, 3. And basically, I should have said this one was g sub y at xy. What would it be for 1, 3? A little louder. 6. 8, which would be 3 over 4, or 0.75. Okay, I hope I'm looking on the wrong, yeah, there we go. 3 over 4, 3/4, got it. I looked on the wrong page and saw negative 1/2. I said, no, 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 I hope that I'm looking in the wrong place, because that can't be right. And it wasn't. This is. Okay. Let's take a look here. Don't know if we'll lose this or not, but let's try. Okay. All right. It took out more than we wanted to. The partial of f with respect to x at the point 1, 3. Wasn't it? That was it, I think it was. So 1 on x and 3 on y. Okay? And the partial with respect to x, we're going to count the 3 constant. Oh, I'm sorry. They're using multiple things. Oh, no, I'm sorry. Okay, here's what we got. Here's the xy axis. Okay. So, obviously, 2 spaces is 1. So there's the 1. 3 would be 1, 2, 3. So every block there is half a space. Okay. And so the partial of that, when y is equal to 3, there's y is equal to 3 there, and the change of this with respect to x would be, you're coming down this way, so it's going downhill, minus 27 over 8. It's not really maybe intuitively obvious that that's the case, but it is a negative number. There's a slope downhill. Now, what 3/4 was the other one. I couldn't remember. Okay. The partial of this function with respect to y when x is 1, when x is 1, you're on this curve, okay? And the change of y with respect to that would be here. As y is increasing, that's increasing ever so slightly. That doesn't look like a one-to-one, but that's because of the orientation here. It's a little bit greater than a one-to-one curve, okay? And you can see it is beginning to go uphill, being pulled up by that. Okay. I don't know if the figures were useful, but that's what they represent. All right, that was example 2. I think we're ready for example. Okay. Wow. Oh no. It seems to me, okay, yeah, they just took 2 extra steps to write this, okay. This is the partial g with respect to y is partial with respect to y of this thing, which is g, which is pulling out your x part up front, and then the partial of this with respect to y, I'm sorry. And that would be this with respect to that 1 over this. So yeah, they got that right, and this is that, so this is 2y times that, everything else. Okay. All right. And then they just plug in the vacuum, just like we did. Okay. Nothing too new there. We had already done it. I think we're ready for example 4. Actually, example 3. They don't do anything with 3 or 4. They jump right to the next thing next. So let's see. Let's do example 3. Goodness gracious, I'm close to dizzy for what's going on here. Compute d by dx, partial with respect to x. It's not a d by d, it's partial with respect to x. That's how you say it. Of this function sine of x squared y to the 5th. Okay. We're taking the partial with respect to x. How would you do this? How would you do it? Where do you start? Say again? Yeah, you use the chain rule, exactly. You're doing with respect to x. So where would you start? Say again? Sine, yeah, you start with the outer function. What's the root of sine? Cosine of the same thing, x squared y to the 5th. But then you do the chain rule for the inner part, and you're doing this with respect to x. What would that give you? 2x y to the 5th. Right, because you don't do anything to the y to the 5th, you treat it as a constant. So, frankly, I think it's a little easier to see, so you don't get confused. Say that 2x y to the 5th times the cosine of x squared y 5th. Okay, it's a square there. It's sort of ugly. All right, that's what we should get. Oh, man. Okay. Let's see whether they finally have the answer. Yeah, there they have it. 2x y to the fifth cosine x squared y to the fifth. Good for them. Okay. Now, we didn't do the partial with respect to y, but I think you see what it would be. Just like this, except in front of it you would have 5x squared y fourth times cosine, the same thing. Okay. Partial derivatives are defined for functions of any number of variables. You can have a whole passel of them. In fact, it's one of the things that sort of aggravates me about some fields. They'll just write down, let's just say, meteorology, okay? They'll say, temperature is a function of solar radiation, wind, speed, wind direction, time of year, blah, blah, blah. So they just keep putting all these independent variables down there, and you have this big, long, hairy, but nothing that tells you how they're related, just it's a function of all those things. And then what you do is take the partials of each at a time and see what that tells you. We're not going that bad yet, but let's go. So let's do example 4. So I think I'll erase this one. Sorry, my head is just beginning to hurt. Calculate this. F sub z evaluated at 0, 0, 1, 1. Obviously, we have at least 4 variables, where f of x, y, z, w, ugly w, and this is equal to e to the x z plus y, e to the x z plus y, it's a plus, it's not showing up too well, divided by z squared plus w. Okay, there's your function. Try to finish this one. I may have to go down and get something to drink because I can't think what else to do. Okay. Let's do this first, huh? Let me go on and try to do this. First, what are we going to do? Yeah, the partial of this thing with respect to z. Meaning that your x, y, even your z and your w are still in the picture, but you treat the x and the y and the w as if they're constants, and the z is the only thing that's your variable. Okay? So, what kind of situation is this? You got z upstairs and downstairs, so guess what? Quotient rule. Right? Now, you could, like I was suggesting before, try to write that as a, with a negative exponent for your denominator and then treat it as a product rule, but it's still messy. So I'd say let's go on and do the quotient rule. Okay? So what would you get? How does that one go? Do you remember? I can't remember. I know I've had 2 of you in a class before, but I don't think I had you in Cal 1. Okay? I never used to say this, but I was tutoring friends of ours who are from India, and he had this one kid, young man, had done his undergraduate in India, gone back to India and stayed with his grandmother and did it in some type of computer engineering was what his undergraduate was. And he was needing to do his the big test. Is that how y'all do it? You don't have these little tests in there. You just do one big test at the end that determines if you're passed or not, right? So he was going to go back and have his math big test at the end of his 4 years undergraduate. He had to know everything about it, and he didn't interact with math all that well. So he wanted tutoring. He'd come over, and so we sat. And this is where I learned to say this. I never had said it anywhere. Instead of derivative of this with respect to this, he said, d-b-d. And he said it so fast, I thought, what is he saying at first? But then I said, what he's saying, d by dx, okay? That's what you're doing. You're doing d by dz, okay? So let's do our, only it's the partial now. So what is the rule for the quotient rule? And this was really fun for the quotient rule. And I think he taught me this one too. Okay, here's, I don't know if you like it this way or not. Low d high minus high d low over low low. Have y'all heard that before? Okay. I guess it's sort of standard. But I hadn't heard it until I tutored him. So what does that, where did it start? Okay. So that would be z squared plus w. Just the denominator times what? Derivative of the numerator. So what would that be? E to the, I think that's a xz plus y. Chain rule it then. That's not a w, it's x, isn't it? Okay, x. All right. There's your low d high minus high d low. That high would be e to the xz plus y times d low 2z. Okay. And that's divided by z squared plus w squared. Low, low. Okay. Now, I'm pretty sure we got a little bit of stuff to do with it, but maybe not. It's okay in that form, I think. And then let's plug in our numbers. 0 for x, 0 for y, 1 for z, and 1 for w. So it shouldn't be too bad. So let's do this now. F sub z of 0, 0, 1, 1. All right. Your z was 1. So this would be 1 squared plus 1. That's 2. E to the 0. So that is just going to be, we won't even write down the e, okay? Because e to the 0 is 1, okay? Times 0. So we don't even mess with the 2, okay? Because it gets multiplied by 0. So then, so the first term completely wipes out. The next term is a minus. And what was that? E to the, that was 1. Times 2z is 2. So that's a minus 2. That's all you got in the numerator, right? Okay. How about the denominator? Okay, that was a 2 squared is 4. So I don't need a parentheses, do I? Okay, just over 4. And that would be negative 1/2. Okay. Don't do more than you have to. And that sure enough came up to negative 1/2. Okay. Now, the next little slide here where in the world is that one from? Must be the next page. No. Where is that from? It may only be in the old edition. Oh, wait. That was from the second part of example 2. Okay. We've already done that. We got our 3/4 there and we're through with that. I was just using this to write them. Okay, good. All right. Here's the next part. Okay. Now, what they're going to do here, if you remember how we started, we said the partial of f with respect to x is equal to the difference here divided by that, right? We didn't quite say it that way. We had an h here and an h there. So we had f sub x at AB was equal to this difference divided by your h, okay? Now we had a limit in there and stuff. So all they've done here is multiply by your h or your delta x. Now, before we just called it h, but you see here the h is the change of x because it's dealing with the x variable. Here the h is the change of y, so they really should have used something else. That's why rather than h you use delta y. So it's just rewriting this sort of in a slope-intercept type form rather than, see, this is sort of your change of y is approximately the slope times the change of x. Change of y is equal to slope of x, except this is change of z. Change of f, slope times change of x. Change of f, slope times change of y. Okay, so that's basically just rewriting that in another form. But these are deltas, not derivatives, not partials. Okay? Now, but notice here in these partials, these partials here, if the x is here, your delta x is here. If there's f sub y here, your delta y is there. And you've got the delta x and y there. Okay. So keep that in mind. Let's do an example 5. Rather bizarre little example, but let's do it. Okay, what we have here, a ball grid array, a BGA, is a microchip joined to a circuit board by small solder balls of radius capital R. Okay, and that's why they say that these solder balls here are radius R. Every one of these has a radius R. Okay. And those are R millimeters, separated by distances of L millimeters. So the distance between any two adjacent solder balls are L millimeters. And what's given here, they say later, L is significantly greater than R. Okay, I don't know where they say that, but it's going to show up somewhere here. Separated by a distance of L, as shown here in this figure. Manufacturers test the reliability of these ball grid arrays, or BGAs, by subjecting them to repeated cycles in which the temperature is varied from 0 to 100 degrees Celsius, basically freezing point of water to boiling point of water, over a 40-minute period. Okay? According to one model, the average N, that's number N of cycles before the chip fails, is, and this is where the problem begins, N is equal to 2200 times capital R, which is the radius of those solder balls, divided by L times D. Well, what is your D here? Where D is the difference between the coefficients of expansion of the chip and the board. Okay? The chip's on top, the board's down there. They may have low difference coefficients of expansion, So that would be the difference between those two. Okay? So that's what your D is. All right. Raised to the 1.9 power. Not quite squared, but fairly close to it. Okay. Estimate the change of N where R is equal to 0.12, D is 10, and L is increased from 0.4 to 0.42. Okay? So basically we've got a delta L here. So that means we need to do a partial of N with respect to L, because we're going to do a delta L. So let's do that one. What would that be? How would you do that? Don't know if it would be helpful, but I'll do this. 2200R over D. We're going to treat that as a constant anyway, aren't we? Please say yes, okay, because you're taking it with respect to L. And then you'll have L to the 1/2, to the minus 1. And all that is being raised to the 1.9 power. I don't know if that's helpful to you. I prefer doing it that way. Okay. Since you're treating the R and the D, everything except the L, as if it's a constant, make it a constant. Okay? And then make L your variable to the minus 1 power, but your whole thing is raised to the 1.9 power. I don't know if that's helpful to you or not. If I do that, what would you give me as your partial? Where do you start? The outer function, right? So that would be 1.9 times all this, 2200R over D, L to the minus 1, to the what? You subtract 1, which is 0.9, right? Now what do we do? Okay, now take the derivative of the inside, chain rule, with respect to L. What does that give you? Negative 2200R over D, L to the minus 2. Done, right? All right, now, I don't know if you like this or not, but let's do it this way. I'm going to pull out the minus sign just to get, because I'm afraid I'm going to forget about it otherwise. Minus 1.9 times 2200 R. Okay, I'm going to substitute in our values here. No reason writing them any longer than I have to. The R here was 0.12, 0.12 over D was 10. Okay, I'll get rid of that real quickly. And your L is still in there, and the L is, okay. The L here is your beginning L, which is a 0.4, okay? 0.4 Okay? And that's raised to the 0.9 power times, I already pulled the minus out, the 2200, and your R was 0.12. I can't write. Over D was 10 again, which again is going to wipe out that one. But this time you have 0.16 because you're squaring that. It's in the denominator. Yeah. Okay. And it asks for estimate the change in N. Okay. So you multiply this by your delta L. Your delta L is 0.02. So you're changing from 0.4 to 0.42. I think that gives you your answer. If you can be careful and do your calculation there. Now, I think what I would do first is do this one first to make sure you only do this to the 0.9 power. Okay? So I would do this. I would say 220 times 0.12 divided by 0.4. That answer raised to the 0.9 power. Multiply that by negative 1.9 by a 220 times 0.12 divided by 0.16 and multiplied by 0.02. See what you get. It's a lot of mess, okay? -272 cycles, negative 272 cycles, okay? Now, there's something there that doesn't sort of make a lot of sense to me. The average number of cycles before the chip fails. What do you mean by negative number of cycles? Does that mean it fails 272 times before you start? I don't know. I mean, that's... oh, no, I'm sorry. Sorry, this is a change. So if your L is increased from 0.2 to 0.4, it reduces the number of cycles before your failure occurs. So if you've made them further apart, that gives you a fewer number of cycles before the fails. Okay. So we got the right answer. It looked like they did it sort of a different way, but we still got the right answer. Same answer. All right. Now, they're doing something else here. Very similar to where we started before. You did what the partial was as a limit. Now they're leaving out the limit part and basically just doing the change of alpha for change of x. That's what partial alpha is. How does F change the change of x? So that is what we're talking about here. And here, they're going back to H rather than delta x. No, fine, sure, I don't know why they don't, but so that would be the difference quotient of alpha of A plus AB minus alpha of AB over H. Okay? That would be approximately what this is. And alpha with respect to Y would be that. You just left off the limit is really all you're doing in making an approximation here. Okay? Now, whether you see any relation to what's coming up here, there is. Whether you see it or not, it is. This is a map. And this is a fairly complicated looking mapping. And what you're doing is the density of seawater, okay? Contour map of the density of seawater as a function of two variables. One of these variables is the temperature of the seawater, and the other is the salinity of the seawater. Now, it seems like we saw a graph of this early on. Those currents. Yeah, this is the graph, contour map that showed the same thing that table showed before. Okay? Or at least similar to it anyway. So your salinity is increasing here from 32.5 to 33 to 33.5. These are parts per thousand, so not a lot of increase, okay? Going up slowly here this way. Your temperature is going up this way, 0 being the freezing point of water, 5, 10, 15, 20, 25 degrees Celsius, where 20 degrees Celsius is about room temperature, so this would be pretty warm for any seawater. You're not going to get a whole lot warmer than that, maybe a little bit, okay? And then here is your density, or then these numbers given like this, okay? Now, what we're to do with that? Estimating the partial derivatives using the contour maps. Seawater density, rho, by the way, in kilograms per cubic meter, depends on salinity, parts per thousands, and temperature degrees Celsius. Use this contour map of seawater density appearing in this figure, figure 4. Yeah. I've lost it. Yeah. To estimate the partial of rho, which is density, with respect to temperature. So how is the density changing per temperature? Well, what they've done here is just going up the temperature scale. You're going from A to B here, just picking those two. The density is changing from 1.0240 to 1.0245. So that density change was a negative 0.0005, right? Per change of temperature, that was from 15 to 17 per 2 degrees. So basically, and I'm going to have to lose this, what you're asking for is your, lost it, to estimate change of density per change of temperature, okay? And in this case, this would be going from those 2 points there. The change of density was a negative 0.0005 divided by, and we decided that was 2 degrees, didn't we? 2 degrees, which would be negative 0.00025. And that would be kilograms per meter cubed per degree Celsius. Okay? And there we have it, negative 0.00025 kilogram per meter cubed degree Celsius. They said kilogram meter to the minus 3 per degree Celsius. It's fine. You see how we did that? Change of density per change of temperature. Did that make sense? Okay. Let's do the second one there, which is asking for change of density per change of salinity. Change of density per change of salinity. And here, we use the change of salinity here and the change of density from here to here. Okay? That's going to take a little more of an approximation here. So your change of density is from 1.0250 to 1.0245. So that's a positive 0.0005. Okay? Do you see that? 0.0005. And then your change of salinity from here to there. Okay? So this is 33.5, 33.6, 0.7, 0.8, 0.94. So that looks pretty close to 33.7, doesn't it? Minus 33, so that's divided by 0.7, or something close to that. 0.7. Okay? Someone with a calculator, punch those in for me. This is a positive number here. 0.000. Is it 3 zeros? Yeah. 714. Okay. We'll leave it like that. And that would be kilogram, I'll write it the way they do, per meter cubed per PPT, part per thousand. Okay? They rounded just to 7. 3 zeros and a 7. I was wondering how much they were going to do. 0.0007 kilogram per meter cubed per part per thousand. Weird units, right? But that's how it changes with that. All right. Can you, okay, whoa, goodness gracious. Skip a little bit here. Let's do what we can to pick up on this. Higher order derivatives, okay? Before we get to Clairaut's theorem, partial of f with respect to x is written like that, right? That's equivalent to the partial of f with respect to x, right? Now, let's just consider that we have two independent variables. You could take another partial, f sub xx, and that would be the partial of, with respect to x, of the partial of f with respect to x, right? Just like we did with derivatives. Make sense? Okay? And this would be written as d2f d, and it's not d's, partial squared. So those mean the same thing, right? And you could do the same. You had the partial of f with respect to y was the same as f sub y, right? And you could do another partial of that, partial with respect to y of the partial of f with respect to y, and that would be f sub yy, and that would be second partial of f with respect to y squared. Okay? So that's what that means. Nothing too new there, right? Before, we'd say f prime and f double prime if these are regular derivatives. We'd say f sub x or f sub y if they're partial derivatives. But what happens if we're taking the partial of this one, the partial with respect to y of the partial of f with respect to x? Can we do that? Yes, we can. This would be the second partial of f, but with respect to y with respect to x. And we keep them in that order. However, our subscript notation would have us f sub x y, because we took the partial with respect to x first, and then took the partial with respect to y. So you see, in this notation, you're working from the left, right to the left, and in this notation, you're working from the left to the right. So these two things mean the same thing. It's this: you take the partial with respect to x, and take the partial of that with respect to y, which is exactly what you did here: partial of f with respect to x, and then take the partial of that with respect to y. But this has the y on the left and the x on the right. This has the x on the left and y on the right. Okay. And then, of course, you could do it the other way up here, too. You could have taken the partial with respect to x of the partial of f with respect to y, which would then be the second partial with respect of f with respect to x and y and then x, because you did the partial y first and then x. And this would have been the same as f sub y x. Okay? Does that seem a little confusing? Guess what? Most of the time these two are equal. It really doesn't matter. Okay? It really doesn't matter. What's that? Well, that's what Clairaut's theorem said. That's why it's on the page here. I'll blow it up a little bit. Okay? Clairaut's theorem on the equality of mixed partials. If L sub xy, that's the partial of f with respect to x, and then you take the partial of y with respect to the partial of f with respect to x, and then take the partial of that with respect to y, and f sub y x are both, if they are both continuous functions on that disk D, remember those disk D's, then the mixed partials are the same. Okay? So yeah, most of the time, if they're continuous on that disk. If they're not, then yeah, they're not equal. But most of the time, we're going to deal with them that are. Okay? And in other words, those two are the same. So it really doesn't matter which order you do. Okay? So there's no real big deal about trying to keep up with that. Now, sadly, we're just about out of time. I said we were going to jump to 15 next, but I want to do examples 7, 8, 9, 10, maybe skip 11. We'll see. But I want to do those examples just so you'll get a practice at doing those. We may not do them all, so we will start next time with example 7. And then once we've done enough of these that you feel confident with them, we'll jump to chapter 15 and do 15 next week. Okay? And I'll probably leave off some of the preliminary stuff that just takes so much time to cover, and then you hardly use it anymore. It's just, well, I should have done it here, but I thought you might need that for your cultural enlightenment. Okay. Any questions? Oh, let me give you a few homework examples in this section. I knew you were hanging around for something. Okay. Do any of the odds 1 through 7. Do either 9 or 11 or both. Do any of the odds 13 to 39. You have a whole portion of those. And then do either 41 or 43 or both. And then you can try 45. That's similar to one we did earlier. And I would say any of the odds 45 through 55. And then hang off and we'll do the others before you do 57. So do a few of those. Good deal. All right, see you Monday. Have a good weekend.